Okay, let's look at. Okay, so here is. We talked about electrical field, right? We talked about how it's away from a positive charge, and you saw in the simulation that it will radially travel outwards. So that means in a circle, basically, you can see that the lines are coming out. An electrical field is basically how strong the field is relative to how much charge it has. So it's defined by this. It's defined by the amount of force over the amount of charge. Okay? Yesterday we defined the force of the force in an electrical field as what? As K, Q1, Q2 over R squared, right? So if the electrical field is the amount of force over the charge, then we can see that Q will cancel out. And what you're left with then is this. It's just a function of K. Now yesterday we defined K as 9 times 10 to the what? 9 times 10 to the 9, right? Newton meter squared per Coulomb squared. So the electrical field is just KQ of the source. So whatever is generating the charge, okay, that's the source, over the distance you are squared from that source. Okay? So this is the electrical field of a point charge, and then we'll talk about a parallel plate. Okay. So all you gotta do is just write down this. You don't have to write down all of this stuff, because we already know what it looks like. Okay. So here is some images. So here is the electrical field, right? Going from a positive to a negative. You can see the field lines. We talked about, at some point it's actually just a straight line. It's not a curve. And then I showed you this picture between parallel plates. Okay. Now the electrical field can also be defined as the voltage over the distance. And I'll show you why. Because we haven't talked about what a volt is, but a volt is the amount of energy over the amount of charge. So if you think about it, before we defined the electrical field as what? Force over Q. And if we do, oops, keep seeing that little thing pop up. Remember what a joule is, right? A joule is what? Force times distance. So then you can see how this would be equivalent, because if a volt is a joule per coulomb, but a joule is force times distance, then you have this. You have force times distance over C. And that's divided by, you can see that's V divided by D. So that gives you F over C, which is the amount of force per charge. So it's equivalent. So if you know the voltage, and you know how far away the plates are, you can figure out the electrical field. It's just a different calculation that you could use, okay? So let's look at an example using this equation. All right, scroll down here. So let's look at number 3, okay? What is the strength of an electrical field of a 10 microcoulomb object at a distance of 10 centimeters? So we don't have voltage here. So which one would you use? Would you use E equals K Q source over R squared, or would you use E equals V over D? Yeah, you would use this one, right? Right? That's the equation you would use. So we have an object. We know K is 9 times 10 to the 9. Newton meter squared per Coulomb squared. The source is 10 microcoulombs, which is 10 times 10 to the negative 6 C, and that's over the distance, which is, it's got to be in meters, 0.1 meters squared. Okay? And you'll notice that, so meters squared will cancel out, and you'll be left with newtons per coulomb. So the electric field is the amount of force over the amount of charge. So, and this is squared. Okay, so what is that? That's 90 times 10 to the 3 divided by 0.01. So that should be 90 times 10 to the 5. Should be 9 times 10 to the 6. 9 times 10 to the 6. Yeah. So it's 9 times 10 to the 6 newtons per coulomb. Okay. So for every one coulomb of charge, and remember, what's 1 coulomb of charge? It's how many electrons or protons? It's 6 times 10 to the 18. So if you have that many excess protons relative to electrons, because this is a positive object, right? So if you have, for every 1 coulomb of charge, then the electrical force that would be generated would be 9 times 10 to the 6 newtons of force for that amount of charge. Okay? Alright, let's look at 4. Let's do this. Let me give myself a little bit more room here. I need to give myself a bit of room. Let me erase this so I can write. Okay. Okay. Alright, let's do this. Okay, next question. We're going to determine the strength of electrical field of a source that has a charge of 50 microcoulomb. We'll say it's positive at a distance of 1 meter. Okay, so what would be the electrical field? So what is it again? It's K Q source over R squared. So that would be 9 times 10 to the, what is it? 9 times 10 to the 9 times Q source, which is 50 microcoulombs, 5 times 10 to the negative 6 over R squared. R is 1. So what would that be? So that would be 450 times 10 to the 3. So 4.5 times 10 to the, was that? Is it okay? So newtons per coulomb. Okay. All right. Now, for that's so determine the strength of electrical field. So this question actually has 2 parts to it, right? The strength of electrical field is the equation KQ source over R squared. If you want to know the force between 2 charged objects, then you would use yesterday's equation, right? So for the second part, we could use this equation. So what would that be? 9 times 10 to the 9 times 50 microcoulombs times 20 microcoulombs over 1 squared. And what do you get for force? What would that be? Is it 9? It's 9? 9 newtons. Okay. Now let's think of a different way we could do that. Because we have the electrical field, right? We know that the electrical field generates a force of 4.5 times 10 to the 5 newtons for every coulomb of charge in the field. So how do you get the force from the electrical field? Now the electrical field is defined as the amount of force over the amount of charge. So we could rearrange that and say that the force is the electrical field times the amount of charge. What's the amount of charge in the field? That's a Q, yeah. I know. Sorry, I used. Are we using capital Q or lowercase Q? I can't remember now. Is it capital Q? All right. I think it's lower. I'm not really sure anymore. Okay. So it's the electrical field was 4.5 times 10 to the what? 10 to the 5 newtons per coulomb. What is the amount of charge in the field? Not the source, but the amount that's actually in the field. Nope. No, because the electrical field is only based on the source. The thing that we will refer to as the source charge. So one of them has to be the source, okay? So the 50 microcoulomb object will be the source. The other one is the object in the field. So we would use the charge of the other object, which would be 20 microcoulombs. Now, if you multiply these two, guess what you get? You get 9. Which makes sense, because there's two ways of calculating that force, right? You can calculate the force by using the equation you saw yesterday, K1 Q2 over R squared, or you calculate the force if you know the electrical field that's being established by something that's charged, and you multiply that by another charged object entering the field, then you know what the force is on that charged object. Okay? So there's just two different ways of figuring out the amount of force. Alright, that's it for today. Then eventually we'll talk about using E equals B over D as a different way to calculate the electrical force. But yeah, it is a catfish. Very scary catfish. So we'll talk about this equation next time. But I wanna save this for later because I do want to talk a little bit more about what voltage means. Okay? Because we use the term voltage, but I want to talk about what it actually means. Alright, so that's it.